Aloha, didn't see you there. In this lab, we're going to be using a shear plate interferometer as a tool for testing radius of curvatures and focal lengths of different optical elements such as lenses and mirrors. So it should be a pretty chill lab, and we're going to walk you through some of the calculations, the beam expander design that we used, and show you how it works. A shear plate interferometer is a simple optical component consisting of a slightly wedged plate of glass with highly polished, uncoated, optically flat surfaces. Reflections on the front and back surfaces interfere to make fringes. Because of the finite thickness of the plate, the front and rear reflections are displaced or sheared with respect to one another, thus the name shear plate interferometer. The beam shear, delta x, depends on the plate thickness t, index of refraction n, and the angle of incidence I. If the plate had perfectly parallel surfaces, an incoming flat wavefront would produce a single uniform fringe because the optical path difference between the front and rear surfaces is constant. If the surfaces are not parallel, but tilted to create a wedge with increasing thickness and height, the optical path difference varies in the vertical direction, producing straight horizontal fringes. Because the shearing interferometer works by comparing the wavefront at two different locations, a spherical wavefront, which is quadratic, produces a wavefront difference that is linear. In the general case of a spherical wavefront incident on a wedged plate, the wavefront difference is linear in both x and y, and the fringes are straight and tilted with an angle proportional to the curvature. Fringe shear plates typically have about 5 to 6 fringes across the aperture, and that's just a trade-off between sensitivity and utility. For sensitivity, of course, it would be desirable to have only one fringe over the whole aperture, but this design allows an individual tester to be usable over a range of beam sizes. But say if a collimation tester is to be used at a specific wavelength for a specific aperture with critical demands in collimation, you can either select a larger aperture such that one fringe will be seen across your aperture, or a custom design that can be made for optimum sensitivity.
So now we're going to look at the theory for our Keplerian beam expander. We need to figure out our collimation lens focal length to determine our beam expansion ratio. And so we can do that over here, where we'll take our original W0 and our F objective, which is given, to get a beam expansion ratio of 50, which means our collimation lens focal length should be 400 millimeters, which is something we have in lab, luckily. Next, we need to figure out the optimal diameter of our spatial filter, so right here. And the way we're going to do that is with this equation right here, just using the wavelength, our focal length, and our W0. And we get an optimal pinhole size of 12 microns, but in lab we don't have that kind of size, so we're going to use a 15 micron size pinhole. So in the first part of this lab, we've got our Keplerian beam expander over here. We've got our shear plate rotated 180 degrees so that when the light is reflected off of this mirror, it's going to reflect up into our shear plate interferometer viewing screen. And we're going to be measuring the fringe spacing, shear distance, and the fringe deviation angle at two different mirror locations.
That's right. When in a situation where you're not able to use the spatial filter size you previously calculated, try and lean towards using a filter size that is larger than the one you calculated. This will not only lead to more light through the filter, but it'll also make it easier to align. However, it will not clean up the beam as good as the optimal filter size.
So now we've flipped our shear plate around 180 degrees and measured our distance the mirror is from the shear plate, the fringe spacing, the orientation of the fringes with respect to the x-axis, and also the shear distance at each location that the mirror was at. We can now calculate the radius of curvature of the wavefront at each location using the shear distance, fringe spacing, wavelength, and the deviation angle. And you'll see we get the radius of curvature at location 1 to be 87 meters, pretty long, and then the radius of curvature of location 2 to be 89 meters. Next, we can use this equation right here, where we're using the radius of curvature of the wavefront and also the distance the mirror is away from the shear plate to then get the focal length of the mirror. Now in this case, you'll see it's a plus or minus. We know that our mirror is a concave mirror, so we're going to add them together. And when we do this, we're going to get a focal length of 96.88 meters, which is really close to the 100 meters that we got, that it's labeled as. And the error may have come from the fractured mirror. So I don't know if you guys can tell from the video, but the mirror had a chunk of glass taken out of it.
So now we're going to do a similar procedure for the test lens. We're going to be using a positive lens, and to measure its focal length and the radius of curvature of the wavefront, we're going to first have to flip the shear plate interferometer around so that the collimated beam is directed up to the viewing screen. Like before, we will use the shear distance, the fringe spacing, we know our wavelength, and the deviation angle. And so that can be used over in the MATLAB script to calculate the radius of curvature, which is 56.9 meters. The focal length of the testing lens is 58.43 meters, which has a 16% error over the listed focal length of 50 meters. And that error could arise from how we took the measurements, I would say. We were measuring the deviation angle with a protractor on top of the viewing screen, as well as the fringe spacing with a ruler. I would recommend either using a camera and measuring that spacing with software, or using something a little more precise than a ruler like calipers. So in terms of the accuracy that we're expecting from these focal length measurements, we were using a protractor to measure the deviation angle on top of the shear plate interferometer and a ruler to measure the distance and the spacing. And so that is reflected by our data that you can see here. We can only get as accurate to say like 0.5 millimeter or so because of the tick marks on the ruler that only allow us to get that far, and say with the protractor, we're only going to the nearest angle.
Okay. We need a freeze frame.
All right, one more take.